This is Coding Math, episode 14, Collision Detection. Today's subject, collision detection, is also sometimes known as hit testing. Collision detection is the term most commonly used in game programming, while hit testing is probably seen more in relation to application UI programming. But basically they amount to the same thing, determining when an object has hit something, or when two objects have hit each other. Collision detection is a broad topic, and there's no single technique or method that handles all of collision detection. It's more of an art than a science, and a lot of times you need to trade off between accuracy and performance. And there's no way I could cover all possible collision detection methods in a single video, but I'll try to cover the overall concept and a few of the most used methods here, and maybe we'll look at some of the more specialized ones on down the line. So basically, collision detection or hit detection is just what its name implies. An on-screen object is collided with, or hit, another object. Sometimes this means that a single object is moved into or onto a certain area of the screen, like the right edge, for example. We've pretty much covered that in episode 12 on edge handling. But usually people think of collision detection as checking to see if two objects have hit each other. Sometimes one of those objects is stationary and one is in motion, sometimes both are in motion, and sometimes one of those objects is actually the mouse pointer. In screen terms, we want to know if any of the pixels of this object overlap any of the pixels of that object. Now, generally speaking, there are two ways to figure out collision detection: mathematically and graphically. Mathematically means that you have some kind of structural definition for each of the objects, some mathematical model that describes their positions and their shapes. And so you can do some calculations to see if those two shapes are intersecting. Graphical collision detection means that you're actually using the defined screen pixels of each object to see if they overlap. This is usually dependent on some kind of built-in method of the bitmaps that you're using in a specific system. For example, on ActionScript, the language used by Adobe Flash, there's a really good bitmap data class that has a hit test method. You can use this to directly compare two bitmaps to see if any of the non-zero pixels overlap, even specifying how much transparency they can have and still register a collision. So this is really powerful, as it allows you to test two complex irregular shapes to see if they're colliding. This would often be totally impractical to do by a mathematical collision detection algorithm, and you wouldn't have that same amount of accuracy. Now, unfortunately, for HTML5's canvas object, nothing like this has been implemented yet. There are some cool features on the way. You might want to check out hit regions and paths. Those are coming, but for now you have to do any pixel-level graphical collision detection by rolling your own methods. This can be complex, it can be CPU intensive, and there's a lot of tricks that are involved. So for now we're just going to stick to mathematical collision detection, and maybe at some other point in the future I'll do another video that covers canvas pixel checking. So on to the mathematical testing. So again, we need some kind of mathematical model of the object or objects that we're testing. Of course, you can have objects with all kinds of shapes, and these can usually be defined mathematically one way or the other, but the more complex your object model is, the more complicated it is to do collision detection with it. So rather than always trying to exactly model an object, first you should see if you can roughly represent it by one of these three shapes: a circle, a rectangle, or a point. These are the objects that we'll cover in this video. Of course, you'll find objects that these just won't be adequate for, but you'll be surprised how many use cases these three objects will cover. So we'll be dealing with four types of collisions in this video: circle, circle, circle point, rectangle, rectangle, and rectangle point. And first we'll do circle, circle. In mini number 5, we cover the Pythagorean theorem and distance. This is vital for this type of collision detection. We'll define a circle as an object having an xy point and a radius. Now, say we have two circles on the screen, and we want to know if they're touching. First, we calculate the distance between them, using the function we created in mini number 5. Now, the radius of this circle is this line segment here, and the radius of this circle is this line segment here. Now, if you add these two together, you can obviously see that they add up to less than the distance between the two circles, and these circles here are obviously not colliding. Now, what about these two? Here's the distance, here's one radius, and here's the other radius. If you add these two radii, their sum is obviously larger than the distance. So here's your algorithm for determining circle-circle collision. Is the sum of the radii greater than or equal to the distance between the centers of the circle? If so, they're hitting. Now in our utils.js file, I've added the distance and distance xy methods we created in mini number 5. I'm now going to add a circle collision method. This will take two objects. We'll assume that these objects are circles and they have xy and radius properties. So in here we can say return distance of c0, c1 is less than or equal to c0 radius plus c1 radius. To save time, I've already created a test file for this called circle.js. It creates two circles, each with a random position and radius. It then sets up a mouse move handler. In that handler, it moves circle 1 to the position of the mouse, and then it checks for the circle-circle collision. If it finds one, the fill style is red. If not, it's gray. Then it draws the two circles. So we run this and move that second circle around, and when the two overlap, bingo, they both turn red. So we get that one down. Next is circle point collision. This is really exactly what we did in the code example in mini number 5. But I'll generalize it here into a reusable function. Back in utils.js, we had a circle point collision method. This takes an x, a y, and a circle object. This method is almost the same as the circle collision method, but it just compares distance to one radius. If you think about it, a point can be a circle with a radius of 0, so this makes sense. I've also set up a test file for this. Again, it's essentially the same thing as we did in mini number 5, but we'll start with a circle object, and we'll use the util method we just created. So again, if the mouse touches the circle, it's red. If not, it's gray. And we can quickly look at that in action, and that works as well. So now on to the rectangle collisions. Rectangles aren't quite as elegant as circles. A rectangle can be defined by 2 points, or by 1 point plus a width and a height. In the latter case, the width and the height are really just offsets from the first point to the second point. We'll go with width height, since that's the convention used by a lot of the other JavaScript methods. Let's start with the rectangle point collision. Say we have a point here, and we want to know if it's in this rectangle. If so, we need to satisfy two conditions. 1, the x position of the point must be within the range defined by the x positions of the 2 points making up the rectangle. And 2, the y position must be in the range of the y positions of those 2 points. It seems pretty simple, so let's try to implement it. We'll create a pointInRect method in the utils.js file. It takes an x, a y, and a rect object. Now we could just do a straightforward implementation here, making sure that the point's x is greater than or equal to rect_x and less than or equal to rect_x plus rect_width. And then we could do the same for y. But I'm going to use this opportunity to make another utility function. We'll call this inRange. InRange will take a value and a range defined by a min and max, and it's just going to return whether or not that value is within that range. Simple enough. We just say value is greater than or equal to min, and value is less than or equal to max. I could have squeezed out a whole mini episode about that, but it would have been a stretch. Now, back in the pointInRect function, we can say return inRange x, rect_x, rect_x plus rect_width. So the range goes from rect_x to rect_x plus width, and x is the value we're testing. And inRange y, rect_y, rect_y plus rect_height. So again, the range is rect_y plus height, and y is the value we're seeing whether or not it's in that range. So if x is in the range and y is in the range, then the point is in the rectangle. If either one fails, then the point must be outside the rectangle. I've created another file, rect.js, that creates a rectangle, listens to mouse move, and checks pointInRect using the mouse position. We can test that, and that seems pretty good. We roll over the rect, it turns red, otherwise it's gray. But let's look at a special case here. Here we have an xy of 100, 100, and the rectangle goes this way with a width of -20 and a height of -10. In this case, if I have a point here, the point is obviously in the rectangle, but it's going to fail the test since its x is less than rect_x and its y is less than rect_y. So we can go back to our code and change these width and height values to negative and see that, yes, this is broken. So there are a few ways to handle this. One is just to say that width and height always need to be positive. That's kind of an arbitrary rule, and it's only going to make this method less useful and more prone to error. Another solution is to create a smart rectangle object that will automatically adjust its XY width height values so that XY is always on the top left and width and height are always positive. That's definitely possible, but what I'd rather do is just have the point and rect function be a little more robust. And that translates into having this in-range function be more robust. Now right now we're checking to see if value is greater than or equal to min. This is assuming that min is less than max. What breaks it is when max is the smaller of the two. So what we really want to know is if value is greater than or equal to the smallest value of min and max. Well, we can use the math_min function for that and say if value is greater than or equal to math_min, min comma max. And on the other side of it, we want to know if value is less than or equal to the largest value between min and max. So we check for value is less than or equal to math_max, min comma max. Now it occurred to me while I was doing this that the clamp method we wrote a little while ago suffers from the same problem. You should be able to clamp a value to an inverted range, but as it is, that's going to break. So we might as well go ahead and fix that now the same way, using math_min to get the smaller of min and max, and math.max to get the larger of them. That's beyond the scope of this video to do a test case for this change, so I'll just write it here, and you should know that I did test it and it does work. Now, just changing this in-range function should have fixed up this inverse rectangle use case, so let's go ahead and test that. All right, this works, so we can move on. Next up is the rectangle-rectangle collision. Now we get a little more complicated. Now, when I was first trying to figure this out, I was kind of struggling for a simple mathematical rule that defines when two rectangles are overlapping. And here's what I came up with. So the left and right x values of a rectangle form a range. We've already seen this with our use of the in-range function. With two rectangles, we have two x ranges. In the same way, we have two y ranges. Now, if the two x ranges overlap each other, and the two y ranges also overlap each other, then the rectangles have to be intersecting. If either the x ranges or the y ranges don't overlap, then the rectangles have to be separate. So first we'll need to know how to tell if the two ranges overlap. It might be easier to say when they don't overlap. So if we have two ranges here, a and b, if the max value of a is less than the min value of b, then there's no way these two ranges can overlap. So for overlap to happen, max of a has to be greater than or equal to min of b. But say we put the range a over here. If the min value of a is greater than the max value of b, there's no overlap possible either. So min of a has to be less than or equal to max of b. So both of these conditions have to be met for an overlap of the range. So we can write a function. Say range intersect min 0, max 0, min 1, max 1. And we return max 0 is greater than or equal to min 1, and min 0 is less than or equal to max 1. And this will work sometimes. But remember our old reverse range problem. We need to account for the possibility that either one of these mins might be greater than its corresponding max. So let's toughen up this function by wrapping everything in math_min and math_max calls. So now we say return math_max min 0, max 0 is greater than or equal to math_min min 1, max 1, and math_min min 0, max 0 is less than math_max min 1, max 1. Now I realize that this starts to read like some kind of tongue twister, but it does make sense. So if you're not totally clear on it, I urge you to take a quick break and sit down with a piece of paper and draw a few ranges and work this all out. Okay, so now we can use this range intersection to create a rect-intersect function. In this we call range intersect twice. Once with the two x ranges, and again with the y ranges. If both of those are true, then the two rectangles must be intersecting. And of course we have a test case for this. It creates two rectangles. One is stationary, and the other one will move with the mouse. We listen for a mouse move event, we get the client X and Y, and set the second rectangle's position offset from that point. We can then call rect intersection on the two rectangles, and if that's true, fill style is red, false, it's gray. And we run this, and it looks like it's working fine. So I urge you to try this with one or both of the rectangles having a negative width or in a negative height to make sure that works as well. I've done so and it does work. Okay, well this episode has gone on long enough, and as you can see, we've only really covered the bare minimum of this subject. So I'm sure we're going to be back looking at different forms of collision detection in the future, and I'll see you then.